Imagine standing on a beach just before dawn. The world is still wrapped in deep blue silence. The air is cool, the waves hush against the shore like a lullaby, and then just a sliver. A thin golden line splits the horizon. In that instant, everything changes. Shadows sharpen. Colors bloom from gray into green, into gold. Birds stir. Your eyes blink awake, not just your body, but your mind. Because in that moment, light didn't just arrive, it spoke. It told you, the world is here, you are here, and you can see it. That's the miracle we take for granted. Every morning, every time we flip a switch, every glance at a screen, every sunset that steals our breath, light isn't just on or off. It's the universe's first language, the original messenger. And yet, how does it actually work? For most of human history, no one knew. We worshipped it, feared it, painted with it, built temples to catch its morning kiss. But we never understood it. Not really, because light refuses to be simple. It dances between worlds, between the tangible and the invisible, the particle and the wave, the past and the present. And the journey to understand it reshaped everything. But before equations, before laboratories, before Einstein scribbled notes that would bend time itself, there was just this, a human being, eyes open, staring into the glow. Think of the first time you saw a rainbow. Maybe you were a child. Maybe you ran toward it, convinced you could touch its colors. Maybe you stood still, awestruck, as if the sky had cracked open to show you magic. That feeling, that quiet wonder is where science begins. Not in textbooks, but in curiosity, in the question whispered under your breath, how? Ancient Greeks thought light streamed from our eyes, reaching out to touch objects like invisible fingers. Others believed it was made of tiny fire particles raining down from the heavens. Neither were right, but both were trying to solve the same puzzle. How can something with no weight, no sound, no smell, paint the entire world in color and shape? Even today, if you hold your hand up to a lamp, you see a shadow. Simple, but think deeper. That shadow exists because light travels in straight lines, until it doesn't, because bend it through water and it paints a rainbow on your wall. Shine it through two slits and it interferes with itself as if it's in two places at once. Light doesn't obey the rules we expect from everyday things. It's not like sand, not like wind, not like anything we can fully hold in our hands. And yet, it's the reason we have sight. The reason photosynthesis feeds forests and oceans. The reason stars aren't just dots, but stories written across billions of years. What we call light is actually a tiny window into a vast invisible spectrum. The colors you see, red, orange, yellow, green, blue, indigo, violet. That's less than 1/10 billionth of all the light that exists in the universe. Beyond red lies infrared, warmth you feel but can't see. Beyond violet, ultraviolet, which sunburns your skin. Then X-rays, gamma rays, radio waves, all of it is light, just different flavors of the same cosmic ripple. But to our eyes, light is personal, intimate. It's the glint in a loved one's eye, the flicker of a candle on a birthday cake. The way dawn turns a city skyline from black to silver. We don't experience light as electromagnetic radiation. We experience it as meaning. And that's where our story must start, not with data, but with awe. Because before we can understand how light works, we have to remember why it matters. For hundreds of thousands of years, humans lived by the rhythm of light. We rose with the sun. We huddled in firelight against the dark. We navigated by stars. Light wasn't just physics, it was time, safety, direction, hope. And when we finally began to ask how it moved, we stumbled into a revolution that would change reality itself. But that journey didn't begin in a lab. It began with a single question, asked by someone just like you, staring into a flame and wondering. Now, let's step back in time, to a world before light bulbs, before fiber optics, before we knew light had a speed. Back when the greatest minds on Earth were locked in a debate that would last centuries and split the very nature of reality in two. Because for a long time, everyone agreed on one thing: light does something impossible. It just wasn't clear what that something was. Picture this: a quiet room in 17th century Europe. Candles flicker, ink stains the desk. Two of the greatest minds of the age sit on opposite sides of a chasm, not of geography, but of imagination. On one side, Isaac Newton, the man who mapped the heavens, tamed gravity, and saw the cosmos as a clockwork machine. On the other, Christian Huygens, a gentle thinker, less famous then but no less brilliant, who believed the universe whispered rather than shouted. And between them, light. Newton was certain. Light was made of particles, tiny, weightless corpuscles shot from the sun like microscopic bullets. Why? Because light travels in straight lines. It casts sharp shadows. It reflects off mirrors at predictable angles, just as a ball bounces off a wall. To Newton, this was obvious. Particles obeyed rules. They were orderly, rational, like the universe he had just revealed with his laws of motion. But Huygens leaned forward, eyes alight with a different vision. What if, he said, light is not a stream of things, but a wave? Like ripples spreading across a pond after a stone is dropped? Waves? The idea seemed absurd at first. Waves need water or air. They need something to ripple through. But space is empty. How could light cross the void between stars if it were a wave? Yet Huygens had a reply. He imagined an invisible ocean filling all of space. An ether, he called it, so fine, so subtle, the planets moved through it without resistance, yet it carried light like wind carries sound. And his theory explained something Newton's couldn't: why light bends slightly when it enters water or glass. Newton called this refraction, and he tried to explain it with forces tugging on particles. But Huygens showed that if light were a wave, refraction happened naturally. The wave slows down in denser material, causing it to change direction, just like ocean waves bend as they near shore. For decades, the debate raged. Newton's reputation was colossal. His word was law. And so, for more than 100 years, the particle theory ruled. Light was a hail of tiny messengers racing from source to eye. Then came a young English doctor named Thomas Young. Not a physicist by trade, just curious. In the year 1803, he set up a simple experiment in his London study. He took a beam of sunlight, narrowed it to a thin thread, and shone it at a barrier with not one but two narrow slits cut side by side. On the wall behind, he expected to see two bright stripes, the shadow of the slits filled with light. But that's not what appeared. Instead, he saw a pattern, a series of bright and dark bands, like zebra stripes painted by ghostly hands. The center was bright, then a dark gap, then another bright line, fainter, then another gap, on and on. This made no sense for particles. If light were tiny bullets, they'd go through one slit or the other and pile up in two clusters. But waves? Waves explain it perfectly. When two ripples meet, they interfere. Where crest meets crest, they amplify bright light. Where crest meets trough, they cancel darkness. This is called interference, and it's something only waves do. Young had just shown that light interferes with itself. The implications were staggering. Light wasn't just particles, it behaved like a wave. The scientific world was stunned. Some dismissed Young as a crank. Others called his experiment frivolous. But the stripes on that wall wouldn't go away. Decades passed. Then, in the 1860s, a Scottish physicist named James Clerk Maxwell, quiet poetic, deeply mathematical. Did something no one expected. He took the known laws of electricity and magnetism, 4 elegant equations, and combined them. And from those equations, light emerged. Not as an assumption, not as an add-on, but as a prediction. Maxwell discovered that changing electric fields create magnetic fields, and changing magnetic fields create electric fields, and together they can sustain each other, racing through space as a self-propagating ripple, an electromagnetic wave. And when he calculated how fast this wave should travel, the number matched the known speed of light, almost exactly 186,000 miles per second. Light, he realized, is electromagnetism, not a particle, not a mechanical wave in ether, but a dance of invisible fields vibrating perpendicular to each other, flying through the vacuum at a fixed, universal speed. The wave theory had won. Or so it seemed, but then the universe threw a wrench into the story. At the end of the 19th century, scientists began studying what happens when light hits metal. They expected the energy of light to build up gradually, like waves washing over a beach, slowly soaking the sand. But instead, electrons shot out of the metal instantly, but only if the light was above a certain color. Red light, no matter how bright, did nothing. But even the faintest blue light, it kicked electrons loose right away. This made no sense for waves. Brighter red light should carry more energy. It should eventually do the job. But it didn't. It was as if light delivered its energy in tiny, indivisible packets like coins, not a stream of water. In the year 1905, a year that would become legendary, Albert Einstein, then an unknown patent clerk in Bern, took a bold step. He looked at the data and said, "What if Newton was partly right after all?" Einstein proposed that light does come in particles, but not Newton's solid corpuscles. These were quanta of energy, later called photons. Each photon carries a specific amount of energy tied to its color. Blue photons pack more punch than red ones. That's why only blue light can eject electrons. It's not about brightness, but about the energy per packet. The physics community recoiled. Waves and particles? That's a contradiction. A thing can't be both. But Einstein didn't flinch. He simply said, light behaves as a wave when it travels and as a particle when it hits something. And experiments confirmed it, again and again. So which is it? Wave or particle? The answer is yes. Light is neither, and both. It is something deeper, something our everyday language can't describe. It is a quantum entity that reveals one face or the other depending on how we look at it. Ask it a wave question, like how do you pass through 2 slits, and it answers with interference. Ask it a particle question, like where did you hit the detector, and it answers with a single point. This duality isn't a flaw in our understanding. It's a feature of reality. And it shattered the classical world forever. So the great debate didn't end with a winner. It ended with a revelation. Light refuses to be boxed. It is not just a tool for seeing. It is a mirror showing us that the universe is far stranger, far more poetic than we ever imagined. And this paradox would lead us to a truth even more astonishing, that light doesn't just move through space and time, it defines them. Close your eyes. Imagine you're standing on a vast empty plain at night. Above you, the stars are sharp and cold. Now imagine you begin to run, faster than a cheetah, faster than a bullet, faster than anything human has ever built. Your feet barely touch the ground. The air blurs. The stars ahead seem to pull closer. The ones behind stretch away. You push harder until, at last, you match the speed of light itself. What happens next? According to everything you've ever known, nothing should change. You'd just be moving very fast. But reality has other plans. because the moment you reach that speed, about 186,000 miles per second time, itself begins to warp. Distances shrink. Light no longer behaves as you expect, and the universe stops making sense. But here's the true shock. You can't reach that speed. Not if you have mass, not even close. Light doesn't just move fast, it moves at the only speed that is absolute in the cosmos, the cosmic speed limit. And this number, this one constant, holds the key to everything. For most of history, people assumed light traveled instantly. Flip a lantern and the room is bright. Strike a match and fire is seen. How could something so immediate have a speed? Even Galileo tried to test it once, standing on a hilltop with a friend, each holding a shuttered lamp. Galileo would flash his light. When the friend saw it, he'd flash back. Galileo hoped to measure the delay, but the distance was too small, the human reaction time too slow. Light crossed the gap in less than a millionth of a second. To them, it was instantaneous. It took a Danish astronomer, Ole Rømer, in the year 1676 to prove otherwise. He wasn't timing lamps. He was watching Jupiter's moons, specifically Io. The innermost of Jupiter's large moons orbits the giant planet every 42.5 hours, like cosmic clockwork. From Earth, astronomers could predict exactly when Io would slip into Jupiter's shadow, an eclipse. But Rømer noticed something odd. When Earth was moving away from Jupiter in its orbit, Io's eclipses happened later than expected. When Earth was moving toward Jupiter, they happened earlier. He realized the light-carrying news of Io's eclipse had to travel farther when Earth was receding, and less far when approaching. The delay wasn't in Io's orbit. It was in the light's journey. And from that, Rømer did the impossible. He estimated the speed of light. His number wasn't perfect, about 220,000 kilometers per second. But it was the first proof that light had a finite speed. Light wasn't magic, it was motion, and motion could be measured. A century later, in a basement laboratory in Paris, a French physicist named Hippolyte Fizeau built a machine that would pin down light's speed with astonishing precision. He aimed a beam of light at a mirror 8 kilometers away, but not directly. First, the beam had to pass through the teeth of a rapidly spinning cogwheel. If the wheel spun just right, the light would slip through a gap on the way out and return through the next gap after bouncing off the distant mirror. If it returned too soon or too late, it would hit a tooth and vanish. By adjusting the wheel's speed until the light disappeared and reappeared, Fizeau could calculate exactly how long the round trip took. His result? About 313 million meters per second. Close. Very close. Then came Léon Foucault, Fizeau's rival, who replaced the cogwheel with a spinning mirror. Light bounced off the rotating mirror to a fixed one and back. If the mirror turned even a hair while the light traveled, the returning beam would be deflected slightly. Measure that angle, know the rotation speed, and boom, you had light's speed. Foucault got it even closer, 298 million meters per second. But the real revolution wasn't in the number. It was in what that number meant. Because unlike the speed of a car, or a sound wave, or a falling apple, light's speed never changes. Not if you're moving toward the source. Not if you're racing away. Not even if the source itself is hurtling through space. This defies common sense. If you drive toward an oncoming car at 60 miles per hour and it comes at you at 60, you see it approaching at 120. Speeds add. But light? No. In the 1880s, two American scientists, Albert Michelson and Edward Morley, set out to detect the ether wind. Remember that invisible ocean Huygens imagined? If Earth moved through it, then light beams sent in different directions should travel at slightly different speeds, like a swimmer going with or against a current. They built an exquisitely sensitive device, an interferometer, that split a light beam in two, sent the halves down perpendicular arms, and recombined them. If light traveled faster in one direction, the waves would be out of sync, creating interference fringes. They saw nothing, no shift, no difference. Light moved at the same speed in every direction, regardless of Earth's motion. The result stunned the world. There was no ether, no universal rest frame, and light's speed was constant, always, for everyone. Einstein later said that this single fact, the invariance of light's speed, was the seed of his theory of relativity. Because if light's speed doesn't change, then time and space must. Imagine two observers, one standing on a platform, another on a speeding train. Both shine a flashlight straight up. To the person on the train, the light goes up, hits the ceiling, comes straight back down. But to the person on the platform, the light traces a diagonal path because the train is moving. Longer path, same speed. The only way both can be true, time runs slower for the person on the train. Just enough so that light still covers the longer diagonal path at the same speed. Time stretches, space contracts, reality bends so that light remains constant. This isn't theory, it's engineering. GPS satellites orbit Earth at 14,000 kilometers per hour. Their clocks run slightly slower due to motion, but slightly faster due to weaker gravity. If engineers didn't correct for both relativistic effects using Einstein's equations, your phone's map would be off by kilometers within minutes. Light speed isn't just a number. It's the heartbeat of space-time. And yet, here's the deepest mystery of all. Why this speed? Why 299,792,458 meters per second? Why not faster, slower? Why is this the universe's speed limit? We don't know. It's woven into the fabric of existence. It appears in Maxwell's equations, in Einstein's relativity, in the quantum vacuum. It's not the speed of light alone, it's the speed of causality, the maximum rate at which any influence can travel. No information, no force, no signal, nothing outruns light. And that makes light the ultimate messenger, not just of sight, but of now. Because when you look at the sun, you don't see it as it is. You see it as it was 8 minutes ago, the time it takes light to cross the 93 million miles to Earth. Look at the nearest star beyond the sun, Proxima Centauri, and you're seeing light that left 4 years ago. Look at the Andromeda Galaxy. That light began its journey 2.5 million years ago when early humans were just learning to make tools. Light doesn't just show us the world, it shows us the past. And its fixed speed means we can never see the universe as it is, only as it was. So when we race against light, we're not chasing speed, we're chasing time itself. And light always wins. But how does it move at all? What is it really, as it flies through the void? No medium, no engine, no friction, just pure self-sustaining energy. To answer that, we must return to a quiet room in Scotland, where a poet with equations in his veins saw the invisible music of the universe. It's a rainy afternoon in Edinburgh in the mid-1800s. Gas lamps hiss softly in the streets. Inside a stone house, a young man with wild red hair and eyes full of wonder sits at a desk cluttered with papers, compasses, and coils of wire. His name is James Clerk Maxwell, and in the quiet hum of that room, he is about to weave light, electricity, and magnetism into a single, shimmering tapestry, one that would redefine reality itself. At the time, electricity and magnetism were seen as separate forces, strange cousins at best. People knew that lightning was electric, that compass needles pointed north because of Earth's magnetism, that wires could spark and batteries could hum, but no one saw the connection. Until Michael Faraday began playing with iron filings and coils of wire in a London laboratory. Faraday, the son of a blacksmith, had no formal education, but he had an imagination that saw patterns where others saw chaos. He noticed that when he moved a magnet through a loop of wire, a current flowed without any battery. And when he ran current through a wire, it created a magnetic field around it. He called these invisible influences fields, a radical idea. To most scientists, forces acted at a distance, like gravity pulling the moon. But Faraday imagined space itself as alive with lines of force, tension, direction, flow. Maxwell read Faraday's notes and saw poetry in them. Where others saw crude experiments, he saw geometry. And he asked, can these fields be described not just with words, but with mathematics? So he began to write, not just equations, but a symphony of them. 4 equations, to be precise, elegant, symmetric, deceptively simple. Together, they captured everything known about electricity and magnetism, and more. The first said, electric charges create electric fields that spread outward, like ripples from a pebble. The second, magnetic fields have no starting or ending point. They always loop back on themselves. There are no magnetic charges or monopoles as far as we know. The third, a changing magnetic field creates an electric field. This explained Faraday's induction. The fourth was Maxwell's own stroke of genius. A changing electric field creates a magnetic field, even in empty space. That last idea was revolutionary. Before Maxwell, everyone thought magnetic fields came only from currents, moving charges. But Maxwell said, no. Even in a perfect vacuum, if an electric field changes, it generates a magnetic field beside it. And that new magnetic field, if it changes, generates another electric field, and so on. Suddenly, electricity and magnetism weren't just linked. They were partners in an endless dance, each giving birth to the other over and over, propagating outward. Maxwell calculated how fast this self-sustaining ripple would travel. He plugged in the known constants, the permittivity of free space, how much electric field a vacuum allows, and the permeability of free space, how much magnetic field it permits. The math gave him a number, approximately 300 million meters per second. He froze. That was the speed of light, known from Fizeau, Foucault, Romer. In that moment, Maxwell didn't just solve a puzzle. He uncovered an identity. Light wasn't something separate from electricity and magnetism. It was them, a traveling disturbance in the electromagnetic field, a wave of intertwined electric and magnetic vibrations oscillating perpendicular to each other, moving forward at nature's ultimate speed. He wrote in his notes, "We can scarcely avoid the inference that light consists in the transverse undulations of the same medium which is the cause of electric and magnetic phenomena." The medium he referred to, the ether, would later vanish. But the core truth remained: light is electromagnetic radiation. This was more than a theory. It was a prophecy. Because if visible light is just one kind of electromagnetic wave, then others must exist. Waves with longer wavelengths, lower frequencies than red light. Waves with shorter wavelengths, higher frequencies than violet. Maxwell had opened a door to an invisible universe. It took 20 years for someone to walk through it. In the late 1880s, a German physicist named Heinrich Hertz was testing Maxwell's equations in his lab. He built a spark gap transmitter, two metal spheres separated by a tiny gap. When he charged them, a spark would jump across, creating a sudden surge of changing electric current. According to Maxwell, this should radiate electromagnetic waves. Hertz set up a receiver, a loop of wire with another tiny gap across the room. And sure enough, when the transmitter sparked, a smaller spark appeared in the receiver, even with no physical connection. He had generated radio waves, light far beyond the red, invisible to the eye, but real as stone. He measured their speed. It matched light's. He showed they reflected, refracted, interfered, just like visible light. Hertz had confirmed Maxwell's vision. The electromagnetic spectrum was real. Today, we live inside it. Your phone's signal, Wi-Fi, microwave ovens, X-rays at the hospital, the heat radiating from your body. All of it is light, just not the kind your eyes evolved to see. What we call light is a tiny sliver, less than 1 octave, in an infinite symphony of electromagnetic vibrations. Red light has a wavelength about the width of a microscopic bacterium. Violet, half that. Radio waves can be longer than a football field, gamma rays smaller than an atom's nucleus. Yet they all travel at the same speed. They all obey Maxwell's equations. They are all, fundamentally, the same phenomenon. This unity is one of science's greatest triumphs. From the warmth of a campfire to the flash of a quasar billions of light years away, it's all electromagnetic waves born from the same cosmic mechanism. And it all began with a man who saw mathematics not as cold logic, but as the language of creation. But here's the haunting part. Maxwell died young, just 48, before Einstein was born, before quantum theory, before we knew light also acts like a particle. He never saw his waves collide with the quantum world. Yet his equations still stand. Even in quantum electrodynamics, the most precise theory ever devised, Maxwell's laws emerge as the large-scale limit. They are as true today as they were in that rainy Edinburgh room. So what is light then, in its purest form? It is a ripple in a field that fills all of space. The electromagnetic field, not made of matter, not made of anything you can weigh, but real, tangible, capable of pushing solar sails, powering photosynthesis, carrying the voice of a loved one across continents. It needs no medium, no ether, no hidden gears, just the dynamic interplay of two invisible forces, self-propelled through the vacuum at the universe's one fixed speed, and this field is everywhere. Even in the deepest void between galaxies, the electromagnetic field exists. Quiet, ready, waiting for a charge to move so it can sing. But then quantum physics dropped a bombshell. Because if you look closely enough, very closely, you find that this smooth waving field is actually made of particles, and not just any particles, photons. Which brings us to the moment light stops behaving like a gentle wave and starts acting like a cosmic rebel. It begins with a piece of metal, just ordinary metal, say, zinc or cesium, sitting in a dark lab. Now shine a light on it, not a laser, not a spotlight, just a lamp. And watch what happens, or rather, what doesn't happen. If the light is red, even if it's blindingly bright, nothing comes out of the metal, no sparks, no current. Silence. But switch to blue light, even the faintest, dimmest blue, and suddenly electrons leap out like startled birds. Instantly, no delay, no build-up, just pop. This is the photoelectric effect. And it broke physics. Because according to Maxwell, according to everything we just learned, light is a wave. And waves deliver energy continuously. A brighter wave carries more energy. So red light turned up high should eventually knock electrons loose. It should just take longer, like filling a bucket with a slow drip versus a hose. But that's not what happens. Bright red light, no matter how intense, does nothing, while even a whisper of blue light sets electrons flying. It's as if light were made of tiny energy coins, and red coins are too small to buy an electron's freedom, while blue coins are just big enough. And the number of coins, that's brightness. But the size of each coin, that's color. In the year 1905, the same year Einstein published his theory of special relativity, he wrote a short, daring paper about this effect. He took a radical idea proposed years earlier by Max Planck, that energy might come in discrete chunks or quanta, and applied it directly to light. Einstein said, light isn't just a wave. It's also a stream of particles, later called photons, each carrying a packet of energy proportional to its frequency. Higher frequency, like blue or ultraviolet. More energy per photon. Lower frequency, like red or infrared, less energy. The equation is simple. Energy equals Planck's constant times frequency. But its meaning is seismic. Light delivers its punch not in a smooth flood, but in individual strikes. One photon, one electron. If the photon has enough energy boom, the electron is out. If not, nothing happens, no matter how many photons you throw. The physics world was horrified. Wave theory had just triumphed. Maxwell's equations were sacred. How could light suddenly be particles again? But the data didn't lie. Robert Millikan, famous for his oil drop experiment, spent a decade trying to disprove Einstein. He built exquisitely precise equipment, measured voltages, frequencies, currents, and in the end, he confirmed Einstein was right. Reluctantly, he wrote, "I spent 10 years of my life testing that equation of Einstein's, and contrary to all my expectations, I was compelled to assert its unambiguous experimental verification." Einstein got the Nobel Prize, not for relativity, but for this, for showing that light has a dual soul. But the quantum weirdness didn't stop there. Remember Thomas Young's double-slit experiment? Shine light through two slits and you get interference, bright and dark bands. A wave thing. Now do it again, but turn the light down so low that only one photon at a time passes through the apparatus. Fire a photon. Wait, fire another. Each one hits the detector as a single dot, a particle-like point. But after thousands of photons, the interference pattern returns. The same stripes, the same wave signature. How? Each photon went through alone. There was no other photon to interfere with. Unless the photon interfered with itself. It's as if each photon in its journey didn't choose one slit or the other. It took both paths at once, a ghostly superposition, then recombined on the other side to create interference. But if you place the detector at one slit to see which way it went, the interference vanishes. You get two clumps. Particle behavior returns. The act of observation, of asking which path, collapses the wave. Light answers based on the question you ask. This isn't philosophy, it's measurable, repeatable, verified in labs worldwide. Even with single electrons, atoms, and molecules, light exists in a liminal state, neither wave nor particle until it interacts. It's described by a probability wave, a mathematical ghost that tells you where it's likely to appear, but not where it is before you look. And this wave doesn't live in ordinary space. It lives in an abstract realm of possibilities, governed by the Schrödinger equation, shaped by boundaries, slits, lenses, and even future choices. In the quantum view, a photon leaving a distant star doesn't follow a single path to your eye. It explores all possible paths, bending around galaxies, looping through space. And only when it hits your retina does it choose a history that fits the outcome. Richard Feynman called this the sum over histories. And it works with stunning precision. So what is a photon? Not a tiny ball, not a little wave packet. It's an excitation, a ripple in the quantum electromagnetic field. Think of the field as an ocean. A calm ocean has no photons. But if you jiggle it, say, by accelerating an electron, you send a ripple outward. That ripple is a photon. But unlike water waves, this ripple is quantized. You can't have half a ripple. You can only add or remove whole units, photons. And here's the kicker. Photons have zero mass. They don't experience time. From a photon's perspective, if it had one, the moment it's emitted is the same moment it's absorbed, even if it traveled for 13 billion years across the cosmos. Distance and duration collapse to nothing. But we don't see that. We see light taking time. Because we're trapped in time. Photons aren't. This quantum nature of light isn't just theoretical. It powers our world. Solar panels? They rely on the photoelectric effect, each photon kicking loose an electron to generate current. Digital cameras? Each pixel counts photons. Low-light photography is literally counting individual light particles. Quantum cryptography? It uses single photons to send messages that can't be eavesdropped on, because any measurement disturbs the photon's state. Even the stability of matter depends on it. If light weren't quantized, atoms would collapse. Electrons would spiral into nuclei, radiating away energy in a death spiral. But because energy is exchanged in discrete steps, electrons occupy stable orbits. Chemistry exists. Life exists. And yet, despite all this, Maxwell's waves still work perfectly for most things. Radio, lenses, mirrors, rainbows. The quantum weirdness hides in the shadows, only revealing itself when you look very closely or very dimly. So which picture is true? Both. Light is a quantum field phenomenon, a reality that transcends classical categories. It is not sometimes wave, sometimes particle. It is something deeper that manifests as wave or particle depending on how we interrogate it. This isn't a flaw in light. It's a limitation of human language. We evolved to track lions and throw spears, not to intuit quantum fields, so we borrow words from our macroscopic world. But the universe doesn't owe us intuitive metaphors. What matters is this: light's quantum nature is not magic, it's math. Precise. Exclusive. Verified to 1 part in 10 billion, the most accurate theory in human history, quantum electrodynamics. And in that theory, light and matter dance in a ballet of creation and annihilation. Photons emitted, absorbed, virtual particles flickering in and out of. Existence in the vacuum. But this dance doesn't happen in isolation. It happens in the arena of space-time itself, which, as Einstein would soon show, is not a stage, but a participant. Because once you accept that light has a fixed speed, you must accept that space and time are flexible. And that changes everything. Imagine you're floating in deep space, no stars nearby, no planets, just you and your spaceship. You turn on a flashlight. The beam races ahead at 186,000 miles per second. Now, fire up your engines and chase after it. Push your speed to half of light's. 3/4, 99%, what do you see? Common sense says the light should appear to crawl ahead, slower and slower as you catch up. But that's not what happens. No matter how fast you go, the light beam still races away from you at exactly the same speed, 186,000 miles per second. This is not an illusion. It's not a trick of measurement. It's how the universe works. And this single, stubborn fact that the speed of light is constant for all observers forces space and time to bend, stretch, and twist in ways that defy every instinct we've ever had. Before Einstein, time was thought to be universal. A second on Earth was a second on Mars, in a speeding rocket or near a black hole. Clocks might tick at different rates due to mechanics, but time itself flowed evenly. A cosmic metronome. Einstein shattered that. In his 1905 theory of special relativity, he started with just 2 ideas. First, the laws of physics are the same for everyone, moving at constant speed. Second, light always travels at the same speed in a vacuum, no matter who's watching. From these, everything else followed, like dominoes falling across reality. Take time. If you're moving relative to me, your clock runs slower from my perspective. This isn't theory. It's been tested with atomic clocks on jets, on satellites, even on fast-moving particles in accelerators. Muons, subatomic particles that decay in microseconds, should vanish before reaching Earth's surface when created in the upper atmosphere. But because they move near light speed, their time slows down from our view. They live longer, just enough to be detected at ground level. From their perspective, time flows normally, but the distance to Earth's surface contracts. Space itself shrinks in the direction of motion. So who's right? Both. There is no true time, no true length, only relationships between observers. And at the heart of it all is light, because the speed of light isn't just about light, it's the speed of causality, the maximum rate at which any event can influence another. If something happens here, it can't affect a place 1 light second away until at least 1 second has passed. Not because of technology, because of the structure of space-time. This creates a cosmic rule. Nothing with mass can ever reach light speed. Why? Because as you accelerate, your energy increases. But not just kinetic energy, your mass energy. As you approach light speed, your effective mass grows toward infinity. Pushing you faster would take infinite energy. Impossible. Only massless things, like photons, can travel at this speed, and for them, time doesn't pass, distance doesn't exist. A photon emitted at the birth of the universe arrives instantly from its point of view, even if, to us, it traveled for 13 billion years. Then, in 1915, Einstein went further. He asked, what if acceleration and gravity are the same? He imagined a person in a windowless spaceship. If the ship accelerates at 9.8 meters per second squared, everything inside behaves exactly as if it was sitting on Earth. Drop a ball, it falls. Stand on a scale, it reads your weight. This equivalence principle led him to general relativity. Gravity isn't a force pulling through space. It's the curvature of space-time itself. Mass and energy tell space-time how to curve. Space-time tells matter and light how to move. And light, though massless, follows these curves. In 1919, during a solar eclipse, astronomers led by Arthur Eddington measured starlight bending as it passed near the sun. The stars appeared slightly shifted, just as Einstein predicted. Light wasn't being pulled by gravity. It was traveling straight, but through curved space. Space-time itself was the lens. This means light doesn't just respond to the universe. It reveals the shape of it. Near a black hole, space-time is so warped that light orbits in circles, the photon sphere. Inside, all paths lead inward. Not even light can climb out. Gravitational waves, ripples in space-time from colliding black holes, were predicted by Einstein in 1916, detected directly a century later, in 2015, by LIGO. And how did they detect them? By measuring tiny changes in the travel time of laser light over 4-kilometer arms. Light, once again, the messenger of the deepest truths. But perhaps the most haunting consequence is this. Because light speed is finite and absolute, the past is not gone. When you look at the moon, you see it as it was 1.3 seconds ago. When you look at the sun, 8 minutes ago. When you look at the Andromeda Galaxy, 2.5 million years ago, when early humans walked the savannah. And when astronomers point the James Webb Space Telescope into the void, they see galaxies as they were just a few 100 million years after the Big Bang. Not models, not simulations, actual light carrying photons that have journeyed for over 13 billion years since the universe was a toddler. That light is real, it's physical, it's here now, striking our detectors. And because of relativity, there is no universal now. Your present is not mine if we're moving or far apart. The universe has no single timeline, only a web of light cones connecting cause and effect. So, in a very real sense, the past is still arriving, still speaking, still visible, And light is the only thing that can carry that message across the gulf of time. This means we are not just observers of the cosmos, we are archaeologists of light. Every sunset is a delayed broadcast. Every star, a time capsule. The night sky is a mosaic of history, not a snapshot of the present. And because light's speed is fixed, we can never see the universe as it is, only as it was. But this limitation is also a gift. Without it, we'd have no window into cosmic evolution, no way to test the Big Bang, no proof that galaxies collide, stars explode, black holes merge. Light's speed doesn't isolate us. It connects us to the past, to the distant, to the unimaginable. And in doing so, it transforms astronomy from stargazing into time travel, not with machines, not with paradoxes, but with eyes, telescopes, and patience. Because to look far is to look back. And the farther we look, the closer we get, not to a place, but to a beginning. On a clear night, step outside, look up. The sky is not a painting, it's a library. Each star, a page, each galaxy, a chapter, and the ink, light older than mountains, older than oceans, older than life itself. That twinkle you see from Sirius? It left when mammoths still roamed the Earth 8 years ago, the faint smudge of the Andromeda galaxy. Its light began its journey when Homo habilis first struck stone against stone, 2.5 million years in the past. And the faintest red dots in the deepest Hubble images. They are galaxies so distant their light has been traveling for more than 13 billion years, emitted when the universe was less than 5% of its current age. We don't need a time machine. We have telescopes. Because light doesn't just show us objects, it shows us moments. And thanks to its finite, unchanging speed, every glance skyward is a glance backward through time. This is not poetic exaggeration. It's engineering. When NASA launched the James Webb Space Telescope, its mission wasn't just to see farther, but to see earlier. By orbiting far from Earth's heat and using a mirror the size of a tennis court folded like origami, Webb catches photons that have drifted across the cosmos since the first stars ignited. These photons are stretched, reddened by the expansion of space itself, shifted from visible light into infrared. But they're real. They carry chemical fingerprints, motion signatures, the glow of stellar nurseries from an era when the universe had no heavy elements, no planets, no possibility of life. And when Webb's sensors record them, we don't just infer the early universe. We receive it directly, physically, like opening a letter mailed at the dawn of time. Think of it, a photon emitted by a newborn star 13 billion years ago zips through intergalactic void, untouched, unaltered. It passes through cosmic webs of dark matter, skirts the gravity wells of invisible halos, crosses epochs of cosmic evolution. And finally, after a journey longer than any story ever told, it strikes a detector made by human hands on a pale blue dot. In that instant, the past touches the present. This is time travel with no return ticket, but it's real. But why can we see so far back? Why hasn't all that ancient light vanished? Because the universe is transparent. For the first 380,000 years after the Big Bang, the cosmos was a seething fog of plasma, so hot and dense that photons couldn't travel freely. Every time a photon tried to move, it scattered off a free electron, like a flashlight beam in thick smoke. Then, cooling as space expanded, the universe reached a critical temperature, about 3000 Kelvin. Electrons slowed enough to be captured by protons, forming neutral hydrogen atoms. Suddenly, the fog lifted. Photons could fly. This moment, called recombination, released a flash of light that filled the entire universe. That light is still here, Stretched by cosmic expansion from visible light into microwaves, it now forms the cosmic microwave background, or CMB, the oldest light we can detect. Discovered by accident in 1965 by two radio engineers cleaning pigeon droppings off an antenna, the CMB is a near-perfect echo of the infant universe. Its temperature is just 2.7 degrees above absolute zero. But in its subtle ripples, variations of 1 part in 100,000, we see the seeds of all cosmic structure, the slight overdensities that would, over billions of years, collapse into galaxies, clusters, and superclusters. The CMB is not a picture of the early universe. It is the surface of last scattering, the farthest wall of light we can ever see. Beyond it, the universe is opaque, like trying to see through the sun's surface. We cannot observe the Big Bang directly, but we can see its afterglow. And that afterglow is light traveling for 13.8 billion years, finally reaching us. Now consider this. Every person on Earth is bathed, right now, in ancient starlight and the whisper of the Big Bang. Photons from distant quasars, from exploding supernovae, from the first generation of stars, all are passing through your room, your body, as you read this. You're swimming in a river of time, but we only see a fraction. Our eyes detect less than 1 octave of the electromagnetic spectrum. To truly read the cosmic record, we need other senses, built by science. Radio telescopes hear the cold hydrogen of early galaxies. X-ray observatories watch black holes devour stars. Infrared eyes peer through dust clouds where stars are born. Each wavelength tells a different era, a different story. Together, they form a timeline written in light. And because the universe is expanding, distant light is redshifted, stretched to longer wavelengths like the sound of a receding siren. The farther away an object is, the faster it recedes, the redder its light becomes. By measuring this redshift, we don't just find distance, we find time. A galaxy with a redshift of 1. We see it as it was when the universe was half its current age. Redshift 10, less than 500 million years after the Big Bang, light becomes a clock. But here's the profound twist. We can never see the entire history of the universe because the universe has a particle horizon, the maximum distance light could have traveled since the Big Bang. Anything beyond that is causally disconnected from us. Its light hasn't had time to reach us. And due to accelerating expansion, driven by dark energy, some galaxies are now receding faster than light can bridge the gap. Their future light will never arrive. We live in a cosmic island of visibility, surrounded by an ocean of unknowable space. Yet within our horizon, light has given us an astonishing gift, a coherent, testable narrative of cosmic evolution, from a hot, dense, beginning to swirling galaxies, to planets, to life. And it all hinges on one fact: light takes time to travel. If light were instantaneous, the night sky would be blindingly bright, every line of sight ending on a star, Orbis's paradox. But because light has a finite speed and the universe has a finite age, the sky is dark. That darkness is proof of cosmic history. So the next time you see a star, don't just admire its beauty. Listen, because it's not just shining, it's speaking from the past, in a language of photons, and after billions of years of silence, it's finally being heard. Light doesn't just show us the universe, it builds it. From the first second after the Big Bang to the rustle of leaves in a forest, light is not a passive spectator, it's an active architect. It carries energy, sculpts matter, sets the rules for chemistry, and even defines the arrow of time. Without light, the cosmos would be dark, yes, but more profoundly, it would be static, lifeless. silent. Because light is the universe's primary means of communication, not just visually, but physically, consider the sun. A sphere of plasma fusing hydrogen into helium in its core. In that furnace, photons are born. Gamma rays at first, unimaginably energetic. But they don't zip straight out. They bounce, collide, are absorbed and re-emitted. A single photon may take 100,000 years to travel from the sun's core to its surface, zigzagging through a dense maze of charged particles. Then, at last, it escapes. And in just 8 minutes, it crosses the void to Earth. That photon doesn't just bring warmth, it brings possibility. When it strikes a leaf, it's captured by chlorophyll. Its energy splits water molecules, fixes carbon from the air, and builds sugar fuel for life. Every calorie you've ever eaten traces back to a solar photon. Every breath of oxygen was released by a plant that harnessed light. Photosynthesis isn't just biology. It's quantum physics in service of life, where a single photon can trigger an electron's leap, starting a chain reaction that sustains ecosystems. Light doesn't just sustain life. It enables perception. Your eyes are photon counters. Rods detect single photons in near darkness. Cones translate wavelength into color. Red, green, blue, painting your world in hues your ancestors used to spot fruit, avoid predators, read emotion in a glance. Vision evolved, not because light exists, but because light carries information, direction, distance, motion, texture, all encoded in the angle, intensity, and color of arriving photons. But light also pushes. Yes, light has no mass, but it carries momentum. When a photon strikes a surface, it imparts a tiny kick. This is radiation pressure. In everyday life, it's negligible. You don't feel pushed by a lamp. But in space, it matters. Comet tails always point away from the sun, not just from solar wind, but from sunlight itself. And engineers have built solar sails, vast, ultra-thin mirrors that catch starlight like wind in a ship's canvas. In 2019, the LightSail 2 mission successfully raised its orbit around Earth, using only the pressure of sunlight. No fuel, no engines, just light, pushing. Even black holes, those monsters of gravity, can be held in check by light. In the hearts of quasars, supermassive black holes devour gas at furious rates. But as matter heats up, it emits so much light that the radiation pressure blows away surrounding material, effectively starving the black hole. Light, in this case, is the brake on cosmic hunger. And light defines the very scale of atoms. Why are atoms the size they are? Why don't electrons spiral into the nucleus? Because of quantum mechanics, but also because of light. Electrons occupy orbitals not by whim, but by the wavelengths of light they can emit or absorb. The energy gaps between levels match photon energies. Shine the right color, and an electron jumps. The wrong color? Nothing happens. This is why gases have signature colors. Neon glows red, sodium yellow. Each element a fingerprint written in light. In fact, all of chemistry is governed by electromagnetic interactions mediated by photons. When two atoms bond, they're exchanging virtual photons, the carriers of the electromagnetic force. The strength of a material, the flow of electricity, the glow of a firefly, all emerge from this dance. Even the vacuum isn't empty. According to quantum field theory, the electromagnetic field seethes with virtual photons, fleeting ripples that pop in and out of existence, borrowing energy from the void. These aren't detectable directly, but their effects are real. They cause the Lamb shift, and tiny energy tweak in hydrogen atoms, and the Casimir effect, where two metal plates in a vacuum are gently pushed together by the pressure of virtual photons outside them. Light, even in its ghostly quantum form, shapes the fabric. of reality. And then there's entropy, the tendency of the universe to move from order to disorder. Light is deeply tied to this arrow of time. The sun is hot, earth is cold. Light flows from hot to cold, carrying entropy with it. This flow powers weather, ocean currents, and life itself. Without this gradient, without light's one-way journey from star to space, the universe would reach equilibrium. No energy flows, no change, no time as we know it. In a profound sense, light is time's engine. But perhaps the most astonishing role light plays is as the universe's ultimate truth-teller, because light cannot lie. When we analyze starlight with a spectrometer, we see dark lines, Fraunhofer lines, where specific elements in a star's atmosphere have absorbed certain wavelengths. Each line is a barcode. From it, we know a star's composition, temperature, motion, magnetic field, even whether it wobbles from orbiting planets. The same technique revealed that distant galaxies are red-shifted, proof of cosmic expansion. The same method detected water vapor on exoplanets, methane on Mars, the aftermath of neutron star collisions. Light carries its history in its frequency, polarization, intensity, and arrival time. And because it travels at the cosmic speed limit, it delivers that history with perfect fidelity. No distortion, no decay in vacuum, just pure information across eons. That's why when we see a supernova in a distant galaxy, we're not just seeing an explosion. We're seeing a standard candle, a known brightness, allowing us to measure cosmic distances. That's how we discovered the universe's expansion is accelerating, a finding that won the Nobel Prize and revealed dark energy. Light doesn't just illuminate the universe, it measures it. So, light is more than a wave, more than a particle. It is a cosmic thread connecting cause to effect, past to present, star to eye, thought to wonder. It is the reason atoms bond, stars shine, eyes see, and telescopes dream. And without it, the universe would not just be dark, it would be mute, still, unborn. You step outside on a sunny day. The sky is blue, grass is green, a red car glides past. This rainbow slice of reality is all your eyes were ever meant to see. But it's a lie of omission, not false, just incomplete. Like hearing only middle C on a piano that spans galaxies. What you call light is less than 1/10,000,000th of the full electromagnetic spectrum. The rest swirls around you, through you, all the time, invisible, intangible, yet utterly real. Right now, as you read this, radio waves from cell towers, Wi-Fi routers, and distant pulsars are passing through your body. Microwaves from your kitchen oven or from the afterglow of the Big Bang are humming in the walls. Infrared radiation. Heat radiates from your skin, your coffee cup, the pavement outside. Ultraviolet rays from the sun are tanning or burning your skin, even through clouds. X-rays from medical machines or exploding stars in distant galaxies pierce the atmosphere. And gamma rays, born in black holes, supernovae, or radioactive decay, are zipping through space like cosmic bullets. You're swimming in an ocean of light you cannot see. This hidden spectrum isn't just more light. It's different kinds of seeing. Take radio waves. Their wavelengths can stretch from millimeters to kilometers, longer than buildings, longer than mountains. They're generated by electrons spiraling in magnetic fields, by lightning, by the cold hydrogen gas between stars. In the 1930s, an engineer named Carl Jansky, working for Bell Labs, was troubleshooting static on transatlantic calls when he discovered a faint hiss coming not from Earth, but from the center of the Milky Way. He had accidentally opened a new window on the universe. Today, radio telescopes like the Very Large Array or the giant dish in China's Fast Observatory Map invisible structures, galactic cores, quasars, the faint whisper of hydrogen from the cosmic dawn. They see through dust clouds that block visible light, revealing stellar nurseries where stars are born in darkness. Then there's infrared below red, wavelengths just longer than what your eyes detect. All warm objects emit it. Your body glows in infrared. So do planets, comets, brown dwarfs, failed stars, too cool to shine visibly. The James Webb Space Telescope is an infrared eye designed to see the first galaxies whose light has been stretched into these longer waves by cosmic expansion. It also peers into dusty disks around young stars, watching planets assemble like cosmic Lego sets. Without infrared, we'd never know how stars form. Because they're born in cocoons of gas and dust, opaque to visible light but transparent to infrared. On the other side of the rainbow lies ultraviolet, beyond violet, shorter wavelengths, higher energy. UV light from hot young stars makes nebulae glow like ghostly lanterns. It's why the Orion Nebula shimmers in photos. But Earth's ozone layer blocks most of it, thankfully, because too much UV shreds DNA, causing sunburns and cancer. Yet some insects and birds see UV. Flowers have UV patterns, landing guides for bees. What looks plain to us is a neon billboard to them. Go further, and you enter the realm of X-rays, wavelengths smaller than atoms, generated when electrons are slammed to a stop or ripped from inner atomic shells. In space, X-rays come from the most violent places, gas heated to millions of degrees as it spirals into black holes, shockwaves from supernova explosions, the coronas of stars. The Chandra X-ray Observatory has shown us a universe seething with high-energy drama, a side of reality invisible to optical telescopes. And at the extreme end, gamma rays, the shortest wavelengths, the highest energy. Born in nuclear reactions, fusion in stars, fission in bombs, particle annihilation near black holes. When two neutron stars collide, they unleash a gamma ray burst so powerful it can outshine an entire galaxy for seconds. And if one happened nearby, it could strip Earth's ozone layer. Yet these bursts also forge gold, platinum, and other heavy elements. We are literally made of stardust, forged in gamma ray fire. But here's the marvel, all of this is light. Radio waves and gamma rays differ only in wavelength and energy. They travel at the same speed. They obey Maxwell's equations. They carry photons, just with vastly different energies. A radio photon might carry a billionth of the energy of a visible photon. A gamma ray photon might carry 1 billion times more. Yet your eyes evolved to see only the wavelengths most abundant at Earth's surface, the peak output of the sun, and the range that penetrates water where vision first evolved. It's a survival band, not a cosmic one. Technology has given us new eyes. Every time we've opened a new window radio, infrared, X-ray, we've discovered something unexpected. Pulsars, quasars, cosmic microwave background, dark matter's gravitational lensing. The universe keeps surprising us because we kept assuming we were seeing all there was to see. Even on Earth, the hidden spectrum shapes our lives. Your microwave oven uses photons with just the right energy to make water molecules spin, creating heat. Through friction. Your remote control sends infrared pulses to your TV. Airport scanners use millimeter waves to see concealed objects. Doctors use X-rays to image bones. MRI machines use radio waves to map soft tissue. And in nature, animals exploit it too. Pit vipers see infrared with heat-sensing pits to hunt in total darkness. Mantis shrimp have 16 color receptors detecting ultraviolet and polarized light we can't imagine. Bees navigate using patterns of polarized skylight invisible to us. We are not at the center of perception. We are one note in a vast symphony. The next time you stand under a clear night sky, remember your eyes show you only the local news. The full story. The epic, multicolored saga of the cosmos is written in wavelengths you'll never see without instruments. But it's there, all around you, all the time. Light is not just what you see. It's what you could see if your eyes were tuned to the music of electrons, the roar of black holes, the whisper of the Big Bang. And in learning to listen, we've discovered that the universe is far stranger, far richer, and far more alive than we ever dreamed. Light seems eternal. It races across voids, outlives stars, carries stories from the edge of time. But even light, pure, massless, timeless, has an end. Not a dramatic explosion, not a fading sigh, but a quiet surrender. A transformation. Because light doesn't vanish. It changes hands. Every photon has a journey and a destination. Most light dies by being absorbed. A photon from the sun strikes your skin. Its energy doesn't disappear. It jiggles molecules, warming you. That energy may later radiate away as infrared light cooler, longer, quieter. Or it might power a chemical reaction in your retina, triggering a signal to your brain. I see blue. In that instant, the photon ceases to exist. Its energy lives on, but as electricity, as heat, as thought. In a leaf, a photon is absorbed by chlorophyll. Its energy splits water, builds sugar, becomes part of a tree, then part of an insect, then part of a bird. The photon is gone, but its legacy grows. In a solar panel, a photon kicks an electron loose, creating current that powers a home. The photon perishes, but its energy lights a room, charges a phone, plays music. This is the fate of nearly all light, not destruction, but conversion. Energy conserved, form changed. The universe keeps perfect books, but some light never meets matter. It flies forever. From the most distant galaxies, photons stream into ever-expanding space. But space itself is stretching. As it does, the photon's wavelength is pulled longer, its energy drained by the expansion of the cosmos. Visible light becomes infrared. Infrared becomes microwave. Microwave becomes radio. And eventually, its wavelength grows longer than the observable universe itself, its energy fading towards zero. This is cosmological redshift, not a Doppler effect, but the stretching of space-time beneath the photon's feet. The photon doesn't slow down. It still moves at light speed. But its identity dissolves. It becomes so cold, so weak, it merges with the background hum of the vacuum. In the far, far future, if the universe keeps expanding, this fate awaits all light. Galaxies will vanish beyond our horizon. Stars will burn out. Black holes will evaporate via Hawking radiation, releasing their last photons in a final whisper. And those photons, too, will redshift into oblivion. The universe will go dark, not because light is destroyed, but because it's diluted beyond recognition. A silent, cold sea of near-zero energy ripples. This is the heat-death scenario, maximum entropy, no energy gradients, no work possible. Light still exists, but with no differences in temperature, no hot stars or cold voids, it carries no information, no change, just uniform stillness. But even then, quantum mechanics leaves a door ajar. According to theory, the vacuum isn't truly empty. It seethes with quantum fluctuations, virtual particles, including photons, blinking in and out of existence. These aren't real, photons you can detect, but their effects are measurable. And in an otherwise dead universe, these flickers may be the last sparks of activity. Some physicists speculate that, given infinite time, a random fluctuation could birth a new universe, a Boltzmann brain, or even a new Big Bang. It's highly speculative, but it suggests that even in darkness, the potential for light remains encoded in the laws of physics. And what of light's ultimate purpose? Perhaps it has none, except to exist, to move, to interact. But in doing so, it enables everything else. Without light's ability to carry energy and information across space, the universe would be a collection of isolated points. No stars influencing planets, no eyes seeing sunsets, no minds wondering about the cosmos. Light is the connective tissue of reality. Even its death is generative. Every time a photon is absorbed, its seeds change, heat flows, electrons jump, molecules form, life stirs. So light doesn't truly die. It transcends. A photon emitted in the Big Bang's fire may now be part of your DNA. A photon from a supernova may have helped trigger the formation of our solar system. A photon reflected off the moon may have inspired a poet, a scientist, a dreamer. Light is the universe remembering itself. And in the end, perhaps that's the deepest truth. We are made of stardust, and stardust is made visible by light. We think with electricity, and electricity is guided by photons. We see with eyes, and eyes evolved because light was there to be seen. Light is not just a phenomenon we study. It is the medium through which the cosmos becomes aware of itself. So when light ends, it doesn't vanish. It becomes part of the next question, the next wonder, the next spark. And as long as there is change, as long as there is difference, there will be light. Not always visible, not always bright, but always present. Because in the beginning was the Word, and the Word was light.